Investigating the relationship between force, mass, and acceleration using simulations. Simon Duchastel. So Newton's second law of motion is important in understanding all motion in the world around us. The acceleration of cars and the collision of a baseball with a bat are good examples of Newton's second law of motion in action. The purpose of this lab is to use a simulation to find the relationship between force, mass, and acceleration, and in order to understand Newton's second law of motion. This is the question this lab will be answering. Materials needed are a computer with internet access in order to use the PhET simulation website, and graphing software such as Excel. The procedure for the first part is to go to the PhET simulation website and choose the motion option. Using the simulation, apply 50 newtons of force for 5 seconds starting from rest to the 40 kilogram object. Note the final velocity and write it down. Repeat this step for each of the objects in succession for 50 kilograms, 80 kilograms, 100 kilograms, and 200 kilograms. Calculate the acceleration from this data by subtracting the change in velocity, which is the final minus 0 because we started from rest, and use this to graph the acceleration versus mass graph. Find a best fit line for this graph. The second part of the procedure is to still go to the PhET simulation website and choose the motion option. And using the simulation, apply 10 newtons of force for 5 seconds starting from rest to the 50 kilogram object. And as before, note the final velocity. And as before, the object starts from rest. Repeat step 2 for 30 newtons, 50 newtons, 100 newtons, and 200 newtons of force, always for 5 seconds with the 50 kilogram object. Calculate the acceleration and also calculate the acceleration by, again, doing final velocity minus 0 from this data and graph the force versus acceleration graph. Find a best fit line for this graph. Here's an example of the procedure for part A. First, I'll set up my timer for 5 seconds. Next, I will activate all of the values for speed, value, and masses. And then I'll select the 40 kilogram girl for the first object. I'll pause the PhET simulation and set the force to 50 newtons. Now I'm ready to start my timer and start the simulation, and once it reaches 5 seconds, I will stop the timer and observe the speed of 6.7 meters per second of the final velocity, and write this down. For part 2, we do the same thing, but with the 50 kilogram box. We set it to pause after having all 4 of the values activated, and put the weight to 10 newtons for the first test. Next, we start our timer and start the simulation, and then after 5 seconds have elapsed, we stop the timer with 1.1 meters per second of the final velocity. Here is the data for part 1 of the simulation. We can see that the trend line is an exponential graph with the equation of approximately 49.99x to the power of negative 0.97, where x to the negative 0.97 is approximately x to the negative 1, which is approximately 45.99 over x. Here in this equation, f of x is the acceleration and x is the mass. For part 2 of the simulation, here is the graph and the data. Here we have the equation 49.99x minus 2.99. Although here f of x is not acceleration, f of x is force, and x is the acceleration. The reason we flip this like this is that it fits nicely with our equation at the end and still shows us the relationship between the force of f of x and the acceleration of x. We can see for our part 1 data that the f of x, the acceleration, and the mass, x, are inversely proportional, where f of x is proportional to 1 over x, or in other words, acceleration is proportional to 1 over mass. For part 2, similarly, we see that the force is directly proportional to the acceleration, or the force is proportional to acceleration. We can also check and see that the coefficient for multiplying the mass is approximately 50. There's a little bit of error, but it's approximately 50, which matches the force that we applied, which was 50 newtons. In the second part, again, it's very, very close to 50, 49.99, which matches the mass we used of the box, which is 50 kilograms. We also have a negative 2.98, which has more error to it, but is relatively close to 0. In conclusion, the data from part 1 shows that acceleration is inversely proportional with mass. The data from part 2 shows that force is directly proportional with acceleration. Because there's the coefficient for both cases was almost equal, minus some error, to the force or the mass that we used, we can also know that there's no coefficient when we put this final equation together. Therefore, we can find the relationship to be F equals ma, or force equals mass times acceleration. This is Newton's second law, which is another way to check this. Possible sources of error for this lab were the timing, since I had to stop the simulation as soon as I saw the timer hit 5 seconds. And sometimes I had a little bit of delay because I had to manage the timer and the simulation. This was very small, however, and our results show this, as they are very close to what you would expect. This answers the question of the relationship between force, mass, and acceleration, as we know now that force is equal to mass times acceleration. We can use this to calculate the motions of many different kinds of objects, as we can see how their change in velocity is affected by the force applied to them, as well as the mass of the object, which governs how all of the objects in the world around us, from very small things such as rocks to very large things such as cars or trains, move around the world.